a pleasure, a real pleasure to have today with us to Professor Daisuke Kawata. Sorry, because I announced him like Dr. Kawata, but he's already a professor in astronomy. Well, Daisuke did his PhD at Tohoku University in Japan, and then moved to Australia at Seymour University, where he spent like almost 4.5 years, no? And well, it was during this time that I met Daisuke for the first time. And well, yeah, we are friends since then. Well, after Australia, no, he got a Japanese research fellowship, and he moved to the Carnegie Observatory in Pasadena, Los Angeles. And he spent a little bit longer there than the fellowship because John Mulcher hired him. No, he didn't want to lose him. And he stayed there until he got a lecture position at the Muller Space Science Laboratory at the University College London, where he's still, I mean, he's been there since October 2008, first as a lecturer and then as a reader, and since 2008 as a 2018, no? As a professor in astronomy, as a full professor. Well, Daisuke has made a lot of contributions to the field of galaxy formation. He has his own, he brought his own code, no, hydrodynamical code, allows him to do numerical simulations and fully cosmological simulations of galaxy formation. And he was one of the first, if not the first, to include like detailed chemical evolution in this type of code, no, in fully cosmological codes. But I also say what he's not on a server as well, and today he's going to talk about observations. Daisuke, I don't know, he's for me, this is one of the nicest persons I've ever met during my whole career. And he's also the hardest worker, and at the same time he's also the last one to leave the party, no? So we had we worked together, we had a lot of fun together, and it's really, yeah, I'm looking forward to know what he has to tell us today. So Daisuke, whenever you want, you can start.
Yeah, thanks, Patricia. That's a great honor to be introduced by the great friend. And yeah, thanks a lot. It's very nice, lots of nice, kind words. So, okay. Yes, it's yeah. Thank you very much for the invitations and this very challenging time for everyone. And I just really appreciate that, Patricia, remembering me still and of our nice time in Australia. And I also realized that Armando is there, and we spent the same time in Carnegie. And nice to see Santi. And yes, we know since he's a PhD student, especially in a PhD I was involved. So it's very nice to see the older friends. And yes, thank you very much for coming, listening to my talk today. And so I will talk about our sort of recent studies in using the Gaia data, which is now quite I'm passionate about. And this is a collaboration with my ex-PhD student, Joe Tuka and Rob Grant. And he's Rob is an MPA, Max Planck fellow, and also the Joe is just finishing a PhD with me, and then she's now in the transition phase to move to the Astro 3D fellow in Austrian National University. And also that I also collaborating with Junichi Baba in National Observatory in Japan, and Andre Migrio and Guy Davis for the astrophysics side, and I would a bit of talk about that in that kind of work with them. So okay, so we go with a pointer somewhere. Okay. So the outline of this talk is, yes, so it's a bit of packed one, but I will make sure that I will finish in 45 minutes. And yes, as everyone knows, in the Gaia is making a big revolutions in the astronomy world. So we'll talk about some, one of the biggest discovery after the Gaia in terms of Milky Way astronomy. And also the how that impact to the galaxy formation in general, and also some work in in observational data, and also neural network, and I also want to talk about future astronomy with future galactic astronomy with future astrometric mission. Okay, so yeah, so well, first of all, I realized that I think Melse Romerogovitz talk about your seminar, about Gaia in your seminar. So probably you already heard about Gaia many times, but I will try to introduce that again. So it's a Gaia. It's launched in 2013, and lots of effort of the Gaia data analysis team made an excellent preliminary release, that data release 1 and 2, and now just you probably remember that in last December, even during the pandemic time, they generously produced this data release 3, early data release 3. And in our institute, MSSL is also heavily involved in the Gaia missions, especially the CCDs calibrated in MSSL, and we did some electric work in the hardware, and also contributed to RBS, radial velocity spectrograph, and also we are part of DPAC for the spectroscopic data processing too. So yeah, our thoughts in passion is with this mission as well. So it's great to see that now everything coming along, and it's just to remind you, the Gaia has three main instruments, astrometry one, and they have lots of CCDs in this is the focal plane, and Gaia is spinning and scanning the sky, all sky. This is the all sky survey, and it starts going through this astrometric field, and then there's some low resolution spectrograph graph called BP and RP, and then there's the RBS, that radial velocity spectrograph is a 10,000 in a resolution. For the bright stars, you can get the radial velocity on it. And so that, yes, these three instruments are now coming along working along very nicely, and producing that excellent data. And yes, I should advertise that. And our MSSL contribution is RBS, and Mark Cropper, my colleague, written about RBS instrument with the data release too. So just advertise that. And yes, so now we have EDR3, early data release 3, but it's everything started from DR1, and which was several years ago. And so I can just show that how it develops, and how this data is changing our view of the Milky Way. And so Gaia data release 1 was astrometric accuracy. We call the parallax. It's just trigonometric parallax. You can get that, and then you can 1 over parallax is basically the distance. And so this kind of accuracy of the parallax, or uncertainty of the parallax, the sigma pi, was 0.3 milliarc second in a data release 1. And the 20% error corresponds to the like a 0.67 kiloparsec, which is basically nearby to the galaxy. So probably this corresponds very close to us. So that this is a sort of Gaia DR1, and then in a DR2, they nailed down to the 40 microarc second level. That's 0.04 milliarc second, and 20% error correspond to like even 5 kiloparsec. It's a huge area. So now we can in the DR2 time, its impact, the revolution really comes, and we could get precise motion and the distance to the stars in a quite large field. And early data release 3 was, in fact, it was quite surprisingly, it's amazing work. It's nailed down to the 20 microarc second, and that's, in fact, it's for the bright stars, you can reach to the 10 kiloparsec away in a 20% accuracy, which was a dream for the Gaia, and it's DPAC is already nailed down it, and even in a preliminary data, and the data had some systematic uncertainties, but that is also reducing, and data gets better and better in the future as well. So that's quite exciting time we are in. Okay. So what's happened? Something happened. Okay. Sorry. Yeah, okay. So this is a picture from the Gaia EDR3, and this Milky Way, and the whole stellar map. On top of that, this white line is showing the motion of the stars in the next 400,000 years. So it's a precise proper motion measured by Gaia really allows us to see that how the stars moves in next in the future, for example. This is just a demonstration, but Gaia is producing now the precise positions and the motions and parallax for about 1 billion stars in the Milky Way. That's also changing our large range of science from the exoplanet to the even cosmology, like H0 gap in Hubble constant map gap. Sorry, the Hubble constant problem. I forgot the word. It's a very nice word. That you probably know. It's also coming from the Cepheid's distance calibration from the Gaia 2. And so this is back to the Gaia DR2, but the Gaia DR2 is quite new thing. The Gaia DR2 is they produce a color from the blue band and the red band of the Gaia spectral photometer, and also they produce the G band, which is overarching this blue to red band and getting photometry. But this is a color magnitude diagram, but it's this y-axis is absolute magnitude using a distance measured from the parallax. So they have decomposed these stars from the using kinematics in a thin disk, thick disk, and halo. And then it's quite a striking thing they found in they already showed that in a DR2 scientific verification paper, in this paper, and that there's a two main sequence in halo stars. So this is a sort of start of time. There's apparently two population in a galactic disk. The galactic halo. So this led to the big Nature paper led by Amina Helmi in 2018 of the discovery of the Gaia Enceladus. And this is the claim. This in the Gaia data, the Prokofiev et al. In 2018 also sort of found that, and in a Gaia DR1, and perhaps the unfortunate name of the Gaia sausage didn't really popularize that. Now it's popular, and but this Gaia Enceladus is it's clearly found in a Gaia DR2. So I just show that in how they found it, and then thanks to the Gaia DR2 and also the radial velocities from the spectrograph, we got the star 6D information, 3 position and 3 velocities, and then you can compute the angular momentum and also energy, the orbital energy. So these all dots are each stars, so you can put in each star's angular momentum and energy. And then you can see the positive angular momentum is basically rotating in the same direction as the disk. So these are disk stars, and these are high energy means less bound, and these are sort of halo stars. But you see this kind of plume of the stars, and so they found that this is sort of a group of stars having a bit of different orbital characteristics. So they pick up these stars, and then so these stars, looking at these stars are chemical compositions. So these are a bit different stars. It's not only the Gaia data, but it's this is from the APOGEE spectrograph. That's the near-infrared spectrograph from the SDSS. But it's a high resolution, so you can get a very nice high accuracy of iron abundance and alpha Fe abundance. And so these are individual stars, FU by H and alpha by V. And you see these black ones are some data from the APOGEE data, and you have these very nice sequence of the thick disk and the thin disk. I will talk about later of the high alpha by V, these thick disk stars, and low alpha by V, thin disk stars. And but these are main Milky Way sort of chemical evolution sequence. But when they pick up these stars, and which is in APOGEE data, and then they found these stars are located in here. So it's a bit off from the main sort of chemical evolution sequence, and they have quite different chemical composition. So they conclude that they have, this is a quite distinguished chemical composition and distinguished kinematical properties. So these must be coming from some other galaxies. And looking at the metallicity and also the how they comparing with the isochrone, and they conclude that it's their age is around 10 gigayear. So 10 gigayear ago, something like a small magnetic size galaxies bombarded or merged to the proto-Milky Way and scattered to our galactic halo. And that is now on the sky, they're distributed like this. And in the press release, they are sort of in the Milky Way, they are having some nice coherent motions, but spread it around in a halo area. So that's Gaia Enceladus, and credits to Cambridge group, and sometimes we call the Gaia Enceladus sausage. And so this Gaia Enceladus sausage, and people follow up, look at the more orbital characteristics, and this is done by the Ted Matles in a 2019 paper, and they look at the eccentricity of the orbit. So they're looking at pericenter and apocenter orbit, and then they're having sort of stars having a quite eccentric orbit. Then they plot that in a blue, and the low eccentricity one is like a more circular orbit. They put in a red, and they see that this Gaia Enceladus sausage populations are having a high eccentricity. And this is the reason why they got the Profeta said the sausage is basically, if you map these stars to the radial velocity in terms of in respect of the galactic center coordinate, the radial velocity versus rotation velocity, these are the they are basically zero rotation, and also having a quite a big velocity dispersion in radial directions. So, and this looks like a sausage in a velocity phase field. So that's why they pick that this name of sausage. Okay, and that looks quite exciting just after the Gaia DR2, and I was listening to the radio when these things appeared, and Jerry Gilmore was saying very nicely, the Gaia basically solved the main aim of the missions to uncover the history of the formation history of the Milky Way in a couple of months after the data release. So this is a nice uncovering the hidden history of the Milky Way formation. So I think it's really nicely said, and the success of the Gaia mission. And but that also reminds us that what we have done in Australia when I was a colleague with Patricia, and Chris Brook and Brad Gibbs and Chris Flynn, and I was looking at the IPARCOS data and noticed that there is a high eccentricity stars and low metallicity stars. And this is the data from Chiba and Bias 2000, and there's some clump of stars there. And turns out that it's basically what the Gaia Enceladus. So this is the 2003 paper from our paper. And yes, it's a data sausage. This is the radial velocity versus rotation. And this V5, this sausage is basically what we are looking at in the 2003 in the IPARCOS data. So it was quite shocking to see that. And we completely forgot about following up this in the DR2 time. So I think we should remember what we have done in 2003 when the data was released. So that was quite tough lesson to learn. But there's some interesting tweak. In this paper, we also said that this clamp is in fact is corresponding to the this clamp found in 1962. So maybe this Gaia sausage is already discovered by the Lindbergh Sandage. This is the quite sort of a seminal paper of the galaxy formation. They claiming that this high eccentricity stars in low metallicity, high eccentricity stars, and also correlation of the low metallicity, high metallicity, low eccentricity stars, basically the evidence of the rapid collapse of the Milky Way. And but we in our 2003 paper, we are saying this is maybe the accretion because this corresponds to this, and in a phase space, it's corresponding like that. So, but now probably this data and these stars in again in the Sandage in 62 could be the part of the Gaia Enceladus. That's probably an interesting historical twist, I think. Okay. So Milky Way had a merger in 10 giga ago. This is probably the last significant merger. We can see that from the current data as archaeological evidence from the Gaia data and the other spectroscopic data. So our question was, yeah, what happened to the Milky Way at that time? And its last significant merger, so must be something to do with formation history of the Milky Way. So that our question is, yes, Milky Way has thin disk and also thick disk, and also bulge and halo bar, and also the stellar halo. And yes, the Milky Way has the thin disk, which is, this is a distance from the galactic plane, and this is the number density of the stars. This is the Gilmour-Reid work, and looking at the number count of the stars, they found that in 1983 even it's the thin disk population and the thick disk population as well. So that's basically you have a very dense thin disk and the diffuse thick disk. And so it's something. What our interest is this impact of the Gaia Enceladus sausage, how they impacted the formation of the thick disk and the thin disk. And but the thick disk and thin disk is also these two populations of the disk is also observed in stellar population as well. And it's a excellent work. It's done by the many years of effort in strong digital sky surveys, and especially the APOGEE near-infrared spectrograph. They can see through the dust and they get a very excellent data for the galactic disk stars. And so this is a sort of footprint of the DR16 of the APOGEE, and this is the work done by the Michael Hayden and in 2015. With this APOGEE data, you can see the stars up to like even 3 kiloparsec, and now DR16 even can go further than that. But this is an interesting, very interesting plot, and we in the Milky Way, what people love to use is you can see now the Fe over H iron abundance versus alpha over Fe in stars in a different place of the galactic disk. So these are disk plane, inner disk, and outer disk. And this, if you go up high, and then you see that the inner disks in stars in high up from the plane, or low down to the plane. So you can interestingly see that there's the two populations. So for example, this is the solar neighborhood, the thick disk population, high alpha over E population, and the low alpha over E population. And it's nicely distinguished. And this thick disk high alpha population is very similar in every way in a disk. And also somehow the thick disk is a bit smaller than thin disk. These thin disk populations go even down to the 15 kiloparsec, but the thick disk populations is disappearing. So maybe thick disk, this high alpha disk is probably slightly smaller in the Milky Way. So that's observational evidence. And so what we wanted to discuss is the Rob Grant is my PhD student is now successfully run that this Auriga cosmological simulations. They run like a 30 quite high resolution Milky Way size galaxy simulation with a moving mesh code called RFO, including gas dynamics and chemical evolutions and star formation and etc. from the cosmological simulations, but changing the initial conditions of the simulations. So, Rob looked at these 30 galaxies and found that some galaxies have sort of a significant merger around redshift 1, and so these are the sort of snapshots in redshift 1.4, 1.3, and 0.9. So that's around 1.0, and also the current d equals 0 snapshot based on an H-ion in a stellar distributions, and these are gas. So the data, so that these galaxies having this kind of mergers around redshift 1, and this is very similar size to the Gaia Enceladus. So we have he has looked at these kind of galaxies, and also noticed that these quite big galaxies are quite gas rich. So they brought gas into this proto Milky Way, and basically induce quite a lot of starburst as well, because this is basically gas-rich merger. So we found that these Gaia Enceladus sausage merger must be a gas-rich merger, and must induce a thick disk and also the halo as well. And we call this the sort of sausage and mash, because they call the sausage, and Rob is a British guy, so we choose it and then put in a title in a monthly notice, but a monthly notice said that this is a too British name, and this is not appropriate for the international journal. So we took, they asked us to take off, so we took off this title from the paper, but it is published now without this name, but we trying to advertise this as a sort of memorable word. Credit to Rob. Okay, so this gas-rich merger can induce a star formation, and so this is the x-axis of look-back time, and so these are high redshift, and this is star formation rate, showing that these are total star formation rate, but then this different colors showing that this red one is a star formation happening in the main Milky Way, and these gray or bluish one is one in happening in the galaxies fell into the Milky Way. And this is the blue, lighter blue ones. The starburst happened during this gas-rich merger. So you can see that this gas-rich merger induced quite the sort of short starburst, and that is also made a thick disk population. And it's also interesting thing is before this merger, this main galaxies star formation rate is keep increasing, and on the other hand, this Gaia Enceladus sausage part is sort of having a flat star formation. So that also explained very well is this low alpha Phi population of the different chemical properties of the Gaia Enceladus sausage progenitor. And because Chris Brook and us also suggested that in this paper, is a constant star formation rate is basically bring down to the alpha Phi. It's a bit lower because type 1a supernovae kicked in with relatively higher than the type 2 supernovae. And but if it's the supernova star formation keep increasing, always type 2 supernovae is dominated, and alpha Phi is kept it higher. And then once they have their star formation rate is settled, and then alpha Phi can decrease because due to the type 1a contribution. So that's this difference in the star formation history also brings this difference in chemical composition between the galactic Gaia Enceladus sausage and the halo stars. So yes, this impact of the Gaia Enceladus sausage, we have looked at the morphology of how they impacted to the structure in redshift 0. So Rob has looked at that and how the starburst population sorry, in this light blue one, the stars formed in this epoch, how they look like. And this is how they look like just after the merger. And these are all stars, and these are rotating components that we call, we have looked at the rotation velocity of them and picking up these disk kinematic stars. And they are a bit more powerful stars, disk stars. And also there's non-rotating ones, more isotropic ones. And there's some halo component also forming that in a galactic center. So this starburst making both inner halo and also quite thick disk. And this is how they look like in redshift 0, and basically the thick disk. And very also these stellar halos formed during the merger also make inner halo as well. And on the other hand, the stars formed before the merger, these red ones, and how they look like is like this. So that before the merger, they already have a quite nice disk type like things as structures. And these are disky component or rotating component. These are non-rotating component. And they already have like a halo stars and disk stars. But in general, they smashed by the Gaia sausage and basically scattered and puffed up. And redshift 0, they are more distributed like halo stars. And so that's called by Vasily Belokov, by him. They said that it is splash component that they're making in a disk, in a halo, but the Paolo Di Matteo and Carve Calat and others also claim that yes, this is basically happening in a different, looking at the different observational data and analyzing observational data in a different way. So, but it's, within this splash component, we think that there is also rotating component, which is basically ended up in a thick disk, and also some of them not rotating is ended up in a halo. So thick disk is basically formed by these starburst and also the scatter by the Gaia sausage. So we think it's sort of a dual origin of the thick disk. So this proto-halo, so proto-halo is this, and the proto-disk is like that. And so this is redshift 0 in the simulations in the FU/H and alpha by phi. This proto-halos, which is a more spherical one, they are sort of the component which is already kicked out from the disk in the previous mergers. So they are more metal poor and high alpha by phi. And the proto-disk one is more recently formed the disk component, but before the Gaia sausage merger. And they also kicked out and then puffed up. And then starburst component is having a more metal rich one. So they make a nice sequence in alpha by phi and high this chemical evolution sequence. And also, this one is showing that the x-axis metallicity and this rotation velocity, and these are thin disk. So the metal poor one, the outer disk rotating faster than the inner disk. And so in the solar neighborhood. And then it's and also thick disk is the metal poor one is rotating slower. But it explained that it's more puffier proto-disk. It's basically in the lower metallicity, it's having lower metallicity and lower rotation. And the starburst one is having a more disky one and having a more metallicity, metal rich. So you can see this kind of the features, which is also observed in the halo, in the galaxy data too. And that you can explain this nice sequence in with this dual origin of the galactic thick disk and thin disk, and also the halos in having a low metallicity and this having a sort of a non-rotation, but supported by the velocity dispersions. Okay. And this kind of thick disk formation really explained very well about this low alpha by phi, low by phi situations. But after that, this kind of a merger happens. After that, the merger finish, and then you can have a nice gas accretion from galactic halo, and that can build up the inside-out thin disk formation. And that is also seen that in Auriga simulation by Loeb, published in 2018. And that's very similar to what we have done. It's a different kind of simulation by Chris Brook in 2012. And just talking about this kind of star formation, galaxy formation history is basically originally Chris Brook suggested that in 2004. And in that very low resolution simulation we have done in redshift 1.4 to 1.0, there are lots of merger happening. This is very natural for the hierarchical clustering due to the lambda CDM power spectrum. And there are lots of mergers happening, but again, these are gas-rich mergers. And in the center, they are forming some geometrically thick disk. And that's the sort of origin of the thick disk. And then after they finish these mergers, then you can grow the really nice thin disk. And that is also seen in a very different simulations done by the other people as well. So that's a quite interesting thing that what you can see in a higher resolution like Auriga is that this thick disk component, when they're forming in lots of mergers, the Milky Way is slightly smaller in terms of total mass. So the hot halo of the Milky Way, proto-Milky Way, is not that hot. So you can have this famous cold mode. So filament from the intergalactic medium can penetrate, and then you can feed the gas in very rapidly. So that's a sort of thick disk phase. And then Milky Way getting bigger, and then filament cannot really propagate. And you can really see that from the Auriga simulations movies, the filament stop being able to penetrate the galactic center. And then sort of this gas accretion, sorry, this is the x-axis is a look back time, and the y-axis is how much gas is accumulated in total. So there's a sort of stagnation period that the sort of gas accretions rate is decreased. And then hot mode kicked in, and then the gas gradually fall into the galactic center within a galactic disk, and you can induce a inside-out galaxy formation. And that's also suggested analytically by my PhD supervisor, Masafumi Noguchi, in a Nature paper in 2018. And so Loeb further look at that and the consequence of the Auriga simulation. They have a quite nice high resolution, so you can really look at the very similar to what you see in the observations in these are FEO by H over alpha Wi-Fi again in the inner disk versus outer disk. And yes, it's still far away from the simulation, the observations, but this is far, far better than what we are doing 20 years ago. So I think it's excellent. The improvement happened in the last 20 years. And so, but the interesting thing is that in the inner disk, this is an observational data, you see this thick disk sequence, and you don't have this metal poor stars. You see that in the outer disk. So the chemical evolution basically goes like this, and we don't see this metal poor stars. And but that's what we see that in the simulation as well. So they basically thick disks formation, cold mode formation happens in the galactic center. And then from the leftover gas, you basically, from these metal-rich gas, you basically make a thin disk stars. So basically you have a sort of a accumulation of the metal-rich and low alpha by phi stars in the galactic inner galaxies. But in outer galaxies, they are much more outer than the galactic thick disk, and so they don't have this kind of formation of this high alpha by phi stars, but they can migrate. There's a radial migration you can induce by the bar or also spiral arm. That's another talk I really like to give you, but it's not. I can talk about that in this talk today. But they can sort of radially migrate and populate here. But when the thin disk getting bigger in the inside-out formation, then they can start making this metal poor stars. That's why the simulation also has the metal poor stars in the outer disk. And that's also consistent with what we see that in observations as well. And that's what we see that in observations. And we see that kind of trend in observations as well. So we have looked at the apogee data again, but with combination of the Gaia astrometry and photometry and 2 mass at the near-infrared ground-based photometric data, and also this is apogee spectra data and stellar parameters. And also we use that in astroseismic data in with our collaboration of the expert in astrophysics. So what we have done is we have just Joe Chuka, my ex-PhD student, constructed this nice tool called the Bingo, the Bayesian infrared inference of galactic archaeology. So nice abbreviation. And she constructed this Bayesian neural network model to predict the age of the stars. So age of the stars are really well measured by the Kepler data, by the astroseismology, because of the stellar pulsation they can see from the light curve, and they can get a very nice age mass measurement, and then comparing with the theory, you can get a nice age. So for the Kepler stars, we got quite a good age estimate. But as you know, the Kepler was looking at the same field for 5 years, and that's only the specific field of the galactic disk. So what we want to have is a age of the stars in a different region of the galactic disk. So we use this Kepler data's age as a training set to train the neural network, and then we try to get the age for the other stars. And what we wanted to use as a sort of input features for the neural network was the apogee data, because apogee has a spectra for the many Kepler data. So we can match that. If the apogee has this kind of properties, showing this kind of properties, these are having this Kepler age. And this is the input feature from the apogee data. So if they set the stellar parameter of log g, TEF, and F over H, mg over phi, C over n, and etc., and then you can make this neural network model and make a prediction of the age. And one thing we have done is she has looked at this weight. So neural network is basically making some nonlinear fitting for the input features to the output level, and making that kind of a nonlinear mixture of that, and then sort of changing this weight in a different combination of this connection to the neurons. And so they usually neural network use that like a gradient descent to nail down this weight. But we can also do is we can just do the MCMC to find out best fitting weight. But if you do the MCMC with penalty functions or maximum likelihood function, then you can also get the probabilities. So that's how we can get the Bayesian neural network. It's very expensive, but you can get uncertainties. And we also, so Joe was very careful with also the balance of the data. And that's what we have to make sure whenever you do the nonlinear fitting. And also we have used that some data augmentation to balance the data distribution. And then once we train that, then we can use this neural network to predict the age for the all other apogee data, because which doesn't have an age from the Kepler, because this neural network is trained to predict the age from the properties obtained from the apogee data. And one thing she has quite careful about it was the sort of the balance of the data, and also trying to eliminate the regression dilution. And they have a so this is done by the AstroN. So that's another neural net, Bayesian neural network code, and that's sort of showing that how they can perform. So this is the true age versus their predicted age, and you see some sort of flattening here. So that's called a regression dilution, because they don't have much data in a very old one or very young ones. So basically, the neural network try to fit in these middle ones, and then basically they try to sort of make some regression of the flat population. They basically weighted too much by the population has a lot of data. So they ended up with some sort of regression dilution. But we weighted, we sort of artificially increased this low young one and older ones and try to make that to flatten it. And so that's what we have done. And that's why we carefully done that. And then we got the age of the stars for the apogee stars. Again, this is from the observations, phi by h plus alpha by phi, and colored by the age. So you can see that in this high alpha by phi population is very older, and then lower alpha by phi stars are younger. And it's an interesting thing in these bridge regions, and we see that it's a sort of age gradient between this. So we think that the sort of Gaia's merger, the starburst component I was talking about, maybe finish around here, and then the inside-out star formation starts happen, and basically build up the low metallicity ones from the metal poor gas accreting from the halo. And in the inner region, just chemical evolution goes metal rich and low alpha by phi. And so we have this inner disk population, but these metal poor one only form the disk once get bigger. So we have this kind of inside and inner region chemical evolution, outer region chemical evolution a bit differently. So it's basically quite consistent with what Rob was seeing that in Auriga simulations. So we are quite happy with that. And but it's an interesting thing is if it's this kind of merger, gaseous merger is happening in high redshift, and then you should expect to see that high redshift galaxy also has a high velocity dispersion. And in fact, an H alpha observation from the BLTs are showing that high redshift galaxies are having a higher velocity dispersion. And but recently, people in Groningen, it's also then showing that it's a ALMA data from the C2 is having a high rotation velocity. So this is a bit opposite. The velocity is but high means low. So this data is coming to this low, but in high redshift ALMA C2 data, it's showing a quite high rotation dominated disk, and which is V over sigma. It's very similar to the local galaxy, disk galaxies. So it's a bit puzzling to see that this kind of cold galaxies, how they can maintain when the galactic disk having a high lot of mergers. And I think I'm running out of time. And but one thing, and just 1 minute, I just wanted to say, it's future missions I'm involving in is JASMINE missions, which is the Japanese near-infrared astrometry missions. And so that's led by the Naoto Goda, and I'm being a project scientist of it. And so this is a near-infrared astrometry missions using 30 centimeter telescope, and led by the selected. Now we are selected by the ISAS JAXA, so we are hoping to launch around late 2028. And we have we target. We cannot do the whole sky survey with 30 centimeter telescope. But we target it to the galactic center, and also when we cannot see galactic center, we will do the transit observation as well. And we basically look at the galactic center and collect that all the lots of data from for the galactic center. And we should have much more stars in the galactic center than the Gaia, and we will try to reach that in a 20 microsecond accuracy. And in the further future is a Gaia near-infrared. It's which is now David Hobbs leading that to the suggesting to the ESA, and it will be we hope that the Gaia successor will be a near-infrared one, but an all-sky survey, and that will be quite exciting. So I will finish here, and this is a summary from my talk. And yes, thanks very much for listening. Thank you.
Thank you very much, Daisuke. Very nice talk. Is there any questions for Daisuke? You can raise your hand. Well, while I'm waiting for questions outside, I have one. For example, in M33 and this M31, also in these galaxies that are farther out, like where we calculate the subpopulation from unresolved stars, we detect there are a lot of old stars, like older than 10 years. So I don't know if you can explain that with the vision of the a small protothick disk that then like grows inside out. I mean, how do you explain that the presence of those all the stars in the outer parts of the disk?
Yeah. So that's
yeah. Sorry. Go.
Yeah, no, yes, that's an interesting puzzle, but it's radial migration is quite efficient. So I think it's that's
you think so? Yeah.
Yes, and
you think that those are migrated stars from the inside?
Yeah, that's if it's diameter rich, and if diameter poor, then of course the halo star can be have a quite nice angular momentum as well. And but if they are like thick disk populations, and then it's quite likely that they are migrated from the inner region. So that's a possibility. Of course, you can have a ring of the star formation in a high redshift and have keeping that, but that's a bit unlikely. But it could be possible, and we may find some galaxies having all ring in outer disk. That could be quite exciting. But in my natural thinking is probably you can bring the quite a lot of stars from the inner disk. Yeah.
Okay, and you think that's due to the spiral arms or to?
Yeah, spiral arm, and then if you have a bar, and that's another thing.
Yeah. Okay.
So that and also in a real galaxy, lots of perturbation going on as well. So you can induce quite a lot of spiral arm from the perturbation of the satellite as well. So and then you can make a quite nice long spiral arm to the quite outer region.
Okay.
And that's what we see that in the Milky Way as well. And you see that quite a lot of wave of the disk in outer disk. Yeah, and probably that's due to the Sagittarius dwarf.
Okay, well, Teresa Antoja has a question.
Yes.
Go ahead.
I will switch on the camera. Hi, Daisuke. It's a long time that I nice to see you. Thank you for the talk. It was very nice. I was wondering if you had a look at the retrograde stars in Auriga, and you do seem to have some. I think a plot in metallicity, angular momentum, or B5. I forgot, but there are some retrograde stars. I mean, yeah, exactly this one, and we do see them in the Milky Way. So have you looked if they are in C2, XC2, or
in a metal rich one or metal poor?
Metal poor, yes. So below the halo, yeah. So you would be at minus 200, right, of Birot. So these are counter-rotating stars. Have you looked at the origin if they are part of the accreted population or?
Yeah, that's quite likely, and we haven't looked at that. And these halo stars are indeed quite. It's quite likely that they formed in a quite early epoch, and then when this final merger happened, they already have a quite a big halo population as well. And when we look at the rotation velocity, they already have a quite isotropic velocity distributions, and it has a quite long tail as well in negative velocities. So I think there are lots of mergers. Of course, there are lots of mergers happened as Milky Way. Of course, we see that quite lots of retrograde moving groups like Sequoia and etc. And so there must be some merger happened in the previously also scattered around and going to that negative velocities. So, but it's also that it'd be interesting to see that these even wet mergers can create quite a high the negative ones, and yes, that would be interesting. But the short answer is we haven't looked at it. But that is indeed interesting questions that how we can make that kind of counter-rotating the stars and very fast rotating stars. But I think there's a lot of different channels, even like negative the gas-rich mergers, or the, as you said, satellite ones, both can be done. And there's a lot of mergers happening in high redshift. So it's not very surprising to see that this kind of populations exist. Yes, but we haven't looked at them specifically to that. It's interesting data. I keep asking lots of questions to Rob, but I think he has lots of things to do. Yes.
Yes, thank you.
David Montes has another question. David?
Yeah, hello. Thanks for your interesting talk. When you start talking about the Gaia Enceladus sources structure, you mentioned abundance of magnesium over iron. Do you know where coming this abundance? Is a particular survey? What precision have these determinations?
I think I had this one.
You saw a plot of magnesium over iron.
Magnesium over iron.
Magnesium or alpha?
Yeah, it's alpha or
no before this.
Before this.
No, it's no problem.
Maybe here. Yeah.
This one, yes.
Yeah.
Where coming these determinations from some particular survey, or? I
think this is this must be APOGEE data.
APOGEE, I imagine, yes.
Have to, use APOGEE data. So yes, it's coming from the APOGEE.
Okay.
And yes, especially from since DR16, I think alpha by phi, alpha, I don't know why, but alpha very good in APOGEE data. So people start looking at MG rather than alpha by phi.
And also later you mentioned the code bingo for determination of age and parameters at the same time. So I imagine this is only useful for giant star, not because it's where the astro-seminar is working well, no?
Yes, exactly. So that's a limitation, and also that we have to use giants because of the basically the input feature we are using is abundance from the APOGEE, and that age-sensitive abundance is basically carbon and nitrogen. So that is mainly driven. So but it's just log G and TEF, of course, and the metallicity also have some contribution, but it's carbon and nitrogen is the main element really affecting age. So we suspect that neural network is basically learning the carbon nitrogen abundance and the age mapping, and basically just some small adjustment by the other parameters. So and the carbon nitrogen is affected correlated age only for the giants. So that's also we have to make sure. And I didn't have a time to talk, but this carbon and nitrogen or even astroseismic age is only reliable for the red giant branch stars, as you said, and also the specific mass of the red clump stars, because the low mass red clump stars, according to the astroseismology people like Andre and the Guy, that they have a mass loss and etc. So they cannot really rely on that age. So they like to cut it. So they are quite conservative, and we can trust them. So so we are doing this cut for that. And also we have another neural network basically trained to pick up only these stars. So because if you apply to the apply this trained network to the old APOGEE data, it can be, as you said, like AGB stars or low mass red clump stars, and but they are not trained to do the neural network. So we use the APOGEE data, Kepler APOGEE data, to pick up only stars which we used for the training. So and then we apply that to the APOGEE data and picking up these stars only, and we try to apply only for that stars. I think that kind of things we really have to be careful. So we shouldn't extrapolate the neural network.
Yeah. Okay. Yeah. And finally, you mentioned also the mission JASMINE. Do you know when this is ongoing? When will be ready to start taking data? Or
Yeah, thank you for asking. I have time to talk about, so I'm glad I can go back to there. And it's recording, right? I shouldn't be able to say much, but that's fine. And our hope is 2028 is our current hope, but there is some competition in Japan for the launch time with, for example, solar missions also approved, and so we may slip off from that, but I'm hoping at 2028. Otherwise, it's a bit science value is a bit of a loose. And so yes, 2028 and 3 years missions, and we hope that we can produce a data catalog like Gaia after several years after the mission. But
okay.
This is not all sky survey, but it's just looking at the same field many times. So this will be a tricky observation, but it'll be very interesting to demonstrate that kind of, we basically take like 100,000 shots and in the same field and try to the decreasing the noise of the astrometry. So I think that in terms of science demonstration, it could be very interesting mission.
Yeah, we hope this going on. Thank you.
Yeah, thank you very much. Yeah, thank you.
I have a last one question as well. During the merger with Enceladus, no? I mean, the picture is that you have the merger and you have the star bars, and then the gas that is accreted later to form the thin disk is pristine gas coming from is pristine gas not coming from the filament that has heated, or you have some outflow. So I mean, to explain the metallicities, do you have to form the thin disk? You have pristine gas heated, or which? Yeah, what are the abundances of that gas?
That's it's an interesting question. It's that's much more detailed than what we have analyzed. Okay. But what we see is it's a sort of a Gaia Enceladus sausage sort of brought this starburst populations. So that's sort of this is the sort of end of the thick disk time, a thick disk formation, and so that also corresponded to our view in here. So that's a sort of thick disk populations formed, and this is a sort of a starburst population. And then that time, it's because of these mergers, the galactic gas disk must be quite chemically well mixed. So having
but it's not mainly gas accreted. It's gas that it was hot because of the merger, and then it's but it's the gas that is in there in the galaxy, no? Because
it's within the galaxies, and yes, not only from that, from the Gaia sausage, but it will be chemically mixed. So I think the chemistry within Gaia sausage won't be very affected by that. But basically, they should mix with a much more big gas reservoir in a protogalactic disk. But the protogalactic disk is quite turbulent, also turbulent driven disk as well. So they must be quite chemically homogeneous. Okay, and that's probably the starting point. And then the gas, metal poor gas fills in. So this gas rich, as a metal rich gas disk, can start generating metal poor stars from the outer disk by the mixing with this metal poor stars. Okay. Sorry, metal poor gas. So you can grow the disk, and you can make a metal poor stars. And so you can establish the metallicity gradient. So what we think is during that merger, the metallicity gradient should be quite flat, or it's basically the same. And one metallicity is basically the same. And then metallicity gradient should establish by the inside out formation. Okay. Yes. So, but that happens should be quite quickly, and. Yes, we are like a giga.
And the starburst, and the starburst is localized, or is because we measured the star formation history in a very localized region of our disk. So I wondering, yeah.
Yeah, that's one question probably for the observer as well. And but it's in the simulation that's probably due to the yeah, the resolution, or of course the physics, the microphysics, and yeah, so we sort of thinking that it's they are chemically homogeneously mixed, and that's what we think that is happening from the data. At least that we don't see that in a thick disk. At least the Milky Way doesn't have a thick disk, the metallicity gradient in a thick disk. So that's.
Go. I was yeah, I mean, my question is, you take the simulations just after the star burst, okay? And you measure the star formation histories in different regions of the disk. I mean, similar distances, but in opposite directions. Do you get similar star formation histories or not? I mean, the gas it can be mixed in shorter time scales, but the stars. I mean, my question is, yeah, the star burst normally, when you have a star burst, normally is localized, no? Because you have, I mean, yeah, in small regions, no? When you have the gas dissipated energy out there. And so my question is, yeah, I mean,
so my view is yes, it's probably not like local starburst galaxies, but in the highest galaxies, there's lots of gas rich multiple merger form going on.
Okay, so
that must be happening in each star forming region must be small, but
but it's happening everywhere.
It can mix very, very quickly because it's basically the potential is not very settled and can have mixing happen very, very quickly. But yeah, sure, if you look at one epoch, probably it's sure that having like a 5 kiloparsec star forming region is quite unlikely. So that's very interesting, important point. In fact, we should expect some well spread region. That's what I think that we really should. Yeah, we really should look at this kind of high resolution simulations and how they should be look like in high resolution galaxies, and that's also done by the lots of efforts and other people as well. But yes, that's quite important thing. But we haven't addressed that. That question is probably not addressed. But looking at the results, that's what I think is happening in a simulation.
Okay, thank you. Okay, is there any other question for Daisuke? Okay, if not, thank you very much, Dais, for that interesting talk. Well, to the rest, thank you for coming, thank you for joining, and we have our next seminar next week on, I don't remember if it's on Wednesday or Friday. I don't know. Well, you get an announcement anyway. I don't have the list right now. So, bye everyone. Thank you. Thank you, Daisuke. Thank you, everyone.
Bye-bye.
Thanks a lot. Nice to see you and hope to see you in person.
Yeah, hope to see you.
Bye.
Yeah. Thank you. Thank you, Patricia.
Thank you, guys. Thank you very much.
Yes. Yeah. Cheers. But I don't know how to log out.
I can.
Okay. Yeah, now I can see. Okay. See you, Patricia. Thanks a lot.
Thank you.
Yes. Bye-bye.
Bye. Vale, pues ya, es que en cuanto yo cierre, cierra todo el mundo, pero ya puedo cerrar, ¿no? Vale.
Tiene que parar el
YouTube.
El YouTube, ¿no?
Pero es que eso lo ha hecho Santi, se ha ido a coger el autobús.
¿Ha salido?
Es que se tenía que ir a las 6, pero tenía que ir a coger el autobús. Es verdad, y no me ha dicho cómo hacerlo, ¿sabéis?
Ahí, tú eres anfitriona de la sesión.
Sí.
Pues a la derecha te aparece una de estas de compartir vídeo, a la derecha del todo creo que es.
A ver, compartir no sé qué, no. A ver, está. Stop live stream, ¿no?
Eso es.